All right, so we're going to consider continuous probability distributions. In probability, particularly if you're taking a calculus-based course, continuous probability distributions are defined by the area under a curve. Now, if you're not in a calculus-based course, then usually you use technology or tables or things like that to calculate these values. But in a calculus-based probability and statistics course, you get at the sort of guts of what's actually going on with those technologies. And what's really going on is you're calculating the area under a curve. There is a function that defines the distribution. And if we integrate that probability curve, that probability, it's usually called a probability density function. If you integrate that over the domain of where it's defined, where it's not zero, that area needs to be equal to 1. We remember from basic probability in statistics that all probabilities, if you add them up, all the possible things that can happen, is equal to 1. The area is like our summation, if you remember from how we defined it in calculus. And so the area under the curve is our total cumulative probability. So what we want to do is, typically these are defined, if they're defined between two particular values, then formally they are defined by a function and then there's zero otherwise. Sometimes these are just given as functions that are defined on a particular interval, and it's understood that what is meant is that these are the non-zero values and everywhere else it is assumed to be zero. So you will often see probability distributions with limits from negative infinity to infinity. Those bounds, those values outside where the particular probability is defined become zero. Integrating a function that is zero is zero. And so when you actually calculate the probability, you substitute only the bounds over which the interval is the function is defined, where the probability distribution is defined. All right, so this is sort of the wind up. This is the probability distributions. Continuous probability distributions are basically a calculus problem, but they have a particular property, that is that the area under the curve is 1. So if we have a function that we would like to use as a probability distribution, we just need to make sure that it scales properly so that it is actually equal to 1 when we integrate it over its region where it's defined. So what we would do, we want this particular shape. We multiply the function by a scalar constant k. We integrate it, we set the result equal to 1, and then we can find the value of k that we would need in order to make this a valid probability distribution. So for example, suppose that I want to model a probability distribution using this function, x squared minus x cubed on the interval 0, 1. If you graph this, you will see that it is all positive, a positive section of the curve. It's 0 on either end at 0 and 1, but it's not 0 and is taking on only positive values in the middle. Those are our conditions for having a probability distribution, the other conditions, that all the values be positive. And so what we want to do is we want to integrate this to verify or to find the value of k that will make this a valid distribution in which the area is in fact equal to 1. So I multiply by k and I integrate it. And since I've specified that it's non-zero, it's defined by this function only on the interval 0 to 1, I'm integrating from 0 to 1. Again, the function is 0 every place else, so I can ignore those. And so when I do my antiderivative, x squared becomes 1/3 x cubed, and x cubed becomes 1/4 x to the 4th. And then I plug in my 0 and 1. And what I end up with is k over 12. And I set that equal to 1. And from there, it's clear that k is going to be equal to 12. If k is 12, 12 over 12 is 1, then I'm good. So my probability function is now actually 12 times x squared minus x cubed. And then I can verify that, in fact, this is the case by just integrating again and showing that it does, in fact, equal 1. So there will be some problems typically in a course like this where you may be asked to find k that will make this a valid probability distribution, or you may simply be asked to just verify that a given function is a probability distribution. Now, the other thing that you have to check, as I mentioned briefly before, is that no part of the function is negative on the interval where you're using it for your distribution. So it's not just that the area is 1, but also that it's never negative on that defined interval. All right, now once we have our probability distribution function and we verified that it is a valid probability distribution, we can then use it to calculate probabilities in that region where it's defined. So I've defined my function on the interval 0 to 1, and so I can find probabilities that represent values, let's say, anywhere on that interval. So if I wanted the probability of being between 1/2 and 3/4, then I can use the distribution and I would simply integrate between those two values. Now, that area is not going to be equal to 1, obviously. It's going to be equal to some value less than 1. But I can go ahead and I can calculate that. And I'm going to end up with a little bit of arithmetic. And I end up with my probability calculation. Now, I can take my regular probability distribution and I can turn it into a cumulative distribution function. And typically we do that by turning it into an accumulation function. Now, a cumulative distribution function defines the probability for x being less than a given value, for your variable to be less than a given value. And so we use a cumulative distribution function. We integrate from the smallest value on which it's defined up to our x variable. And then we integrate the function, the probability distribution, using a dummy variable because x can't be two things in the problem at the same time. And when we do that, what we get is a function involving x. And then anytime we plug a value of x into the problem, then it will give us the probability up to that point. So between whatever the lowest value is and that value. So using the example that we used before, I'm integrating 12, what was x squared minus x cubed, but now it's 12t squared minus t cubed. And if I integrate that, I plug in 0 for my lower bound because that's where the non-zero part of the distribution is defined, up to x. And I end up with this function 4x cubed minus 3x to the 4th. Now, if I wanted to find the probability that x is less than, let's say, 1/4, then I would simply plug in 1/4 into this function, into this cumulative distribution function, and it would give me the value of that probability. Now, if I want to recalculate my previous example for between two functions, I can also use the cumulative distribution function. I can simply plug in the upper bound, the value less than 0.75, and then find the value less than 0.5 and subtract that off. And I should get the same result that I had before. Now, the last use of the cumulative distribution function is going to be to calculate either percentiles or medians, or things like quartiles and so on and so forth. So typically this is going to not work out mathematically necessarily very simply. In a lot of problems, you'll have to do this numerically. You'll have to dig into a calculator and to solve these problems. But some textbook problems will give you values that are easy to solve by hand, and some distributions work better than others. But let's say I wanted to find the median, then I would set my cumulative distribution function equal to 0.5. Now, I could do this with, using the definition as well, using the original f of x, but then I would have to set my entire integral equal to 0.5 anyway. So it's better to find the cumulative distribution first and then set that equal to 0.5. And so I've done that here to solve for the median. I've set this equal to 0.5, and I graphed this in order to find the value. This is my cumulative distribution. It starts out at 0 and goes up to 1, because anything less than 1 in this distribution should, that is the whole probability of the whole distribution. So for the cumulative distribution, the area is not 1, but you start out at 0 on one end and then you go up to 1 on the other end. But where this cumulative distribution function intersects with 0.5 is when x is equal to 0.6143. So that is the value of the median. That is the point at which 50% of the probability is less than that value and 50% of the probability is greater than that value. And that is somewhere between 0 and 1, so that makes sense. And it's close to the middle. This isn't a perfectly symmetric distribution, so it's not exactly at the middle, but it is close to the middle. Now, on the other hand, if I wanted to find the 90th percentile, then I would set my cumulative distribution function equal to 0.9. So it works basically the same way. And again, if I do this numerically using my graph, this is my cumulative distribution function, this is my 0.9 value. They intersect when x is 0.8574. So that means that 90% of the time, if I'm using this probability distribution, 90% of the time I will get a value at or below 0.8574. So that is sort of the basics behind continuous probability distributions and their basic properties using calculus.